All right. So we're going to take a look at Chapter 5 now, Chemistry 3101, and this deals with stereoisomerism. So one of the main things you're going to learn from this chapter are going to be what's called the Ingold pre-log rules. Okay, and this is designating what we call a stereocenter as being R or S. It's one of the major things that you learn in this chapter, besides other content as well. But anyhow, let's get into it. So you guys already know what isomers are. Isomers are compounds that have the same formula, but they're two different compounds. So for example, constitutional isomers, we've seen this several times in chemistry. Um, it says here constitutional isomers have the same molecular formula, but different connectivity of the atom. So let's say you had a formula like C2H6O. There's two possible ways you could organize that. You could have ethanol. So you could have ethanol. Ethanol, come on. I guess it's going to erase. Okay, let's try that again. Okay, so we could have C2H6O. That could be ethanol, CH3, CH2OH. Okay, so ethanol is one possibility from that formula. And then we could also have CH3OCH3, and this is called dimethyl ether. Okay, so these compounds have the same formula, C2H6O, but they have a different connectivity, and so they have different boiling points. Okay, for example, the boiling point of ethanol is something like 76 degrees Celsius, and the boiling point of dimethyl ether is like negative 23 degrees Celsius. So they have huge differences in their boiling points, so they're obviously different compounds. Then if we move on to what are called stereoisomers, which is going to be the focus of this chapter, they have the same molecular formula and constitution, but a different spatial arrangement of atoms. So this is the key word here, is that the atoms have a different arrangement in space. And I'll give you some quick examples of that. Let's say you had trans 1,2 dichloroethylene, this compound here. And let's say you had cis 1,2 dichloroethylene, right? Both of these compounds are going to be CHCl, CHCl, right? And I could actually fix this. Let me put the double bond in here. Okay, son of a gun. Anyhow, if I put this like this, I have my double bond like this. Okay, both of these compounds have CHCl, double bond CHCl, right? There's no arguing that. But are these two compounds identical? No. One of them is a trans compound and the other one is a cis compound. And so they have the same molecular formula, same constitution, but the arrangement of atoms in space in 3 dimensions is different in the two of them. So although the two molecules that you have shown here have the same connectivity, they are not identical, right? If you look at both of these compounds, right, they both are a 6-membered ring, a cyclohexane, and then we have 2 methyl groups on them, CH3, CH3, right? They have the same connectivity. However, the arrangement of the methyl groups or the atoms in space is different. And so we say that they are stereoisomers, right? Different arrangements of atoms in what? Space. Okay, and the first one, the 2 methyl groups are on the same side of the ring, but on the other one, they're on opposite sides of the ring. So again, they both have this connectivity. The order of connection of the atoms is the same, but the arrangement of the atoms in space is different. And so we say that they are stereoisomers. Okay, we say they're stereoisomers. And when we have stereoisomers, we have to give them unique names because these two compounds are going to have different melting points, different boiling points, et cetera, et cetera. They're different compounds. So one we call it cis 1,2 dimethyl cyclohexane, and the other one we call it trans 1,2 dimethyl cyclohexane. Cis for the 2 methyl groups on the same side of the ring, trans for the 2 methyl groups on opposite sides of the ring. So going back to the idea of cis and trans with a double bond, you remember that when we have a carbon-carbon double bond, we do not have free rotation because we have overlap of the p orbitals. And so if we take a look at cis-2-butene and trans-2-butene, these two molecules have the same connectivity, don't they? They both are CH3CH double bond CH CH3. They have the exact same connectivity, don't they? But are they the same compound? No. They have a different arrangement of the atoms in space, and therefore they are stereoisomers. In one of them, the two methyl groups are on the same side of the double bond, so that one is cis. And on the other one, they're on opposite sides of the double bond, and so they are trans. So again, to repeat for the third time, stereoisomers have the same order of connection or connectivity of the atoms, but the arrangement in 3 dimensions is different, and so we say that they are stereoisomers. So cis and trans is one type of stereoisomerism. There are several types, but remember, we can have cis and trans with a double bond, and we can also have cis and trans with a ring. Okay, so now that we've established that, let's try a problem. It just says here, identify the following pairs of compounds as either constitutional isomers, stereoisomers, or identical structures. So let me fix this line here. We'll do something like this, okay, and then like this. We'll break this one up like that. Okay, so there you go. So we have 5 different pairs of compounds. So if I look at the one in the top left, okay, we're asking, are they constitutional isomers, stereoisomers, or identical structures? So for this one, can anybody identify these compounds? Would these be identical? Would they be stereoisomers? Would they be constitutional isomers? So yeah, thank you. These two compounds are identical, aren't they? So these are identical. Okay, the only difference is that the chair has been flipped. Okay, we just flipped the chair. So in one, the hydroxyl is axial, and on the other one, it's equal. So those two are identical. They have the exact same connectivity. Okay, what about these two here? These two alkenes, would those be identical, constitutional isomers, or stereoisomers? And again, it's not a trick question. Go with your gut on this one. Anybody have an idea about this one? If we were to put a line here, and if we were to rotate this 180 degrees, what would we end up with? We'd end up with this, okay, our double bond, and we'd have our bond down like this. So you can see that these two compounds are, you can see that those two compounds are identical. So we'll put identical here, and we'll put identical here because we solved those ones. So let's see, line this up. Okay, let's try these two diols here. And the first one, you see that this hydroxyl is going up and this hydroxyl is going up. This one is up and axial, this one is equatorial. But now in this one, this hydroxyl is up and axial, but this hydroxyl is down. But the two hydroxyls are 1 carbon apart, right? 1, 2, and 1, 2. So could anybody tell me what would be the best definition for these? Would they be constitutional isomers, identical, or stereoisomers? These two. What would be the best definition for these two? Anybody? These ones would be stereoisomers. That's right. So stereoisomers. They have the same connectivity, but they have a different arrangement of the atoms in space. On one, the two hydroxyls are cis, and on the other one, they are trans. So they are stereoisomers. All right, if we look at this one here, it's again in the same vein as the last one. We have one hydrogen going up here. We have one hydrogen going down here. So this is a trans compound. And on this one, we have a hydrogen going up, and we have another hydrogen on the exact same side. Okay, so this one would be cis. Could anybody tell me what would be the best descriptor for these? Would they be identical, stereoisomers, or constitutional isomers? Yes, they're stereoisomers. Exactly, stereoisomers. All right, in the last one, we have two compounds that have the same molecular formula. Both are C4H8O, but they have a completely different connectivity of the atoms. And so these two compounds are just constitutional isomers. They have the same formula, but they're just constitutional isomers. That's all they are. All right. Let's see if we can identify these compounds as being cis, trans, or neither. Well, we've already looked at these, so I won't spend too much time on this. You can see in this one, the two protons are on the same side of the double bond. And so this is a cis alkene. On this one, you have one hydroxyl going up, the other one going down. And so this is a trans compound. This one, this hydroxyl is going up and this hydroxyl is going up. So this is a cis compound. This hydrogen is going up. This hydrogen is going down. So this is a trans compound. And just as a reminder, whenever you have a double bond, and on one of the carbons, if the two groups are identical, so here we have a methyl and here we have a methyl, it's neither cis nor trans. It's impossible to say, you know, it's cis or trans. So for this one, it would be neither cis nor trans, right? Because this methyl group is trans to this one, but this methyl group is cis to this one. So it's not a cis or trans compound, this compound. All right, so there we go. So that's a little bit about stereoisomers, but cis-trans that we just covered in detail, cis-trans in a ring, and cis-trans in a double bond. So we'll put here ring, ring, or double bond. That's only one type of stereoisomerism. There are other important stereoisomeric relationships. And to identify such stereoisomers, we have to be able to identify what are called chiral molecules. So we have to be able to identify chiral molecules and a chiral object. So first we'll start with a chiral object, and then we'll get into a chiral molecule. A chiral object is an object that is asymmetric. And what that means is that it's not superimposable on its mirror image. So I want you to remember that phrase, not superimposable on its mirror image. If I take a look at these glasses here, okay, where both of the lenses are inside, you see that if I was to take this pair of glasses, right, this pair, you can see that they are superimposable on the other ones, right? I could pick these ones and I could plop them right on top and they would match perfectly. So we see that these are superimposable. But if I take this pair of glasses here, okay, and if I just redraw them, okay, I'll redraw this pair. I'll draw them like this, and we'll say you got something that looks like this, something that looks like this. Okay, if I was to rotate that 180, or sorry, 180 degrees, we would see that the shaded in lens would end up over here. And now if I try to take those glasses and put them over these ones, you see that they don't overlap. The clear lens ends up on the shaded one, and the shaded one ends up on the clear one. So these are not superimposable, okay? And so we say that these glasses here are chiral, okay? Whereas these glasses here are achiral. They are not chiral. So chiral means not superimposable on its mirror image. Another example would be the human hands, right? If you hold up your two hands next to each other, you see that they are mirror images. They look identical, but if you put them one on top of the other, you see that they are not superimposable, right? On your, you know, a left-handed glove is not going to fit your right hand, for example. So the human hand would also be something that is chiral. So why is chirality important in molecules? It's because if you have two chiral molecules that are mirror images, they're going to have many identical properties, okay? If you have two chiral molecules that are mirror images, okay, I'll underline here, molecules that are mirror images, they have many identical properties, meaning they're going to have the same melting point, the same boiling point. Their infrared spectrum is going to look identical. Their mass spec is going to be identical, etc. Okay. However, here's where it gets crazy, is that their pharmacology can be very different. That means that one compound might be, you know, some kind of medication, whereas its mirror image could cause you to get sick, okay, or die. Okay, so this is very, very important because the receptors on our cells are chiral, and so they can distinguish between two molecules that have the same connectivity, yes, but different arrangement of atoms in space. And so visualizing molecules and mirror images is manipulating in 3 dimensions can be very difficult. And so it says here absolutely critical that you use handheld models. I would say strongly suggested, okay? And you don't have to get an expensive model kit. You'll see mine is nothing fancy. And so if we take a look at these two molecules here, okay, you can see that we have a black sphere in the middle, okay, and then it's connected to a red, a white, a green, and a blue, okay? So if we take a look at this and we take a look at its mirror image, okay, we see that these two molecules have the same connectivity, don't they? They have a carbon connected to a hydroxyl, an ethyl, a methyl, and a proton. However, if you try to overlap these two molecules, you will see that they are not the same, okay? They are not identical. So I'm just going to grab my model kit here and show you. Just bear with me here for a second while I switch over to my camera. So if I switch over to my camera here, here is a molecule. So you see you have a black sphere connected to just waiting for my camera. Okay, you see a black sphere connected to a blue, an orange, a white that's in my fingers, and a yellow, okay? And then if I grab this one here, I have the same thing. I have a black connected to a blue, an orange, a green, and a white, or a yellow and a white, okay? If I put the two like this, you can see that they are mirror images of each other, okay? However, if I try to overlap them, okay? Now the way I have them oriented here is you see the blue and the orange overlap, but if you look at the green or the yellow and the white, they do not overlap, and you can see that over here as well. And if you're thinking, well, Mr. Dion, you're just holding it the wrong way, you're not doing it right, okay? Well, I can tell you I am doing it right, and it doesn't matter how you hold these molecules. If you look at these two mirror images, okay, you say, oh yeah, they're going to overlap. You can try to overlap them, and you can see now that the yellow and the orange overlap, but now the blue and the white don't overlap. Okay, there's nothing you can do to make these overlap. So what's the conclusion? They are both black connected to an orange, a yellow, a white, and a blue. So they have the same connectivity. However, is the arrangement of the atoms in space identical? The answer is no, they are different. And so these are two different compounds. They're going to have the same melting point, boiling point, IR, MS, and all that stuff, densities, etc. However, on a receptor, they're going to react differently in terms of pharmacology. Why? Because the receptors on our cells can recognize the difference between the two non-superimposable mirror images. So those are chiral molecules. So let me go back to my screen here. Just bear with me. All right. So with that in mind, we see that through the use of handheld models, we can prove that these two compounds, even though they have the same connectivity, they are not identical. And so we would say that this is a chiral molecule, and we would say that this is a chiral molecule. Well, a little more on chiral molecules. How do you recognize when an atom is chiral? Okay, it says here when an atom like carbon forms a tetrahedral center, so meaning it's sp3 hybridized, okay, and it's attached to four different groups, okay, four different groups, not atoms, four different groups, okay, we call it a chirality center. And so if we look at this carbon here that's highlighted in green, okay, if I draw this carbon here, what is it connected to? It's connected to a chlorine, it's connected to a hydrogen, which isn't shown in the bond line structure. It's also connected to a methyl group. Okay, here we have a methyl group, and it's connected to a ethyl group, right? This is an ethyl group here. So is it connected to four different groups? Yes. Okay, sometimes students will say, well, no, this is a carbon and a carbon. They're identical. It didn't say atoms. It said four different groups. This, what I have in the blue circle, is a different group than what's in the red circle. Okay, give me a thumbs up if you're with me on that. Everybody with me on that idea? Okay, cool. So now that we have that, we can see that this is a chiral carbon. Well, I can tell you that if you have a CH2 group or a CH3 group, those are never chiral. Okay, it's impossible, right? They're attached to two hydrogens, at least one of them's attached to three, and those are identical. And so if you have a CH2 or a CH3, those are never chiral. So this is not chiral, this is not chiral, this is not chiral, right? You have two CH3s and a CH2, all right? So if we look at this molecule here, the next one, If I highlight this carbon in red, why is it chiral? It's attached to a hydroxyl. It's attached to a hydrogen, which is not drawn. It's attached to an ethyl group on one side, over here, that's an ethyl group. And then it's attached to a propyl group over here. So is it attached to 4 different groups? The answer is yes. So is that carbon in green chiral? Yes. Nothing else is a chiral center because this is a CH2, this is a CH3, et cetera, et cetera. And so that carbon highlighted in green is the only chiral carbon. Let's try one more. Okay, the carbon highlighted in green here is chiral. Why? Because it's attached to a bromine, it's attached to a hydrogen. On one side, it's attached to a carbon that is sp2 hybridized. And on the other side, this side here, it's attached to a carbon that is sp3 hybridized. Those are 2 different carbons. And so it's attached to 4 different groups. And so is that carbon chiral? The answer is yes. Why is this not a chiral carbon? This one here, because this is sp2 hybridized. It's not attached to 4 different groups. So give me a thumbs up if you're with me on recognizing a chiral carbon. 4 different what? Groups. Yeah, so it's not just atoms, it's 4 different groups. And we always travel until we find a point of difference. So it says how many chirality centers are in each of the following compounds. So we'll start with this compound here. This is just cyclohexanol. Keep in mind that there's a hydrogen in the axial position here. So are there any chiral centers in this molecule? The answer is no. So here there are no chiral centers, no chiral carbons, okay? Why can I say that? You might think, well, this carbon is attached to 4 different groups. No, it's not. It's attached to the hydroxyl and the hydrogen. Then here we have a methylene. Here we have a methylene. So no point of difference. Let's keep going. Here we have a methylene. Here we have a methylene. No point of difference. Here we have a methylene. And so the path this way and the path this way are identical. So there's no point of difference. And so it's not attached to 4 different groups. So there's no chiral center in this compound, and therefore this compound is achiral. Okay, so we'll put here this compound is achiral. So it's an achiral compound. All right. What about this one here? Could anybody tell me, are there any chiral centers in this molecule? And it's not a trick. Are there any chiral centers in here? In this cis-1,2 cyclohexane diol be the name of this compound. Are there any chiral centers in it? I want to ask you, this carbon that I have highlighted in red, is it chiral? Is that carbon highlighted? Yes. So that carbon in red is chiral. How do we know? Let's take a look. The carbon highlighted in red, okay, I'll make a list in red. So it's attached to a hydroxyl. It's attached to a hydrogen. Right here, it's attached to a CH2 group, which we call methylene. And then here, it's attached to a carbon that has a hydroxyl attached to it. So it's attached to a carbon with a hydroxyl and a hydrogen on it. So it's attached to 4 different groups. So that red carbon is a chiral center. And for the same reason, this carbon is a chiral center, right? That carbon in blue is attached to a hydroxyl, it's attached to a proton, it's attached to a CH2, and it's attached to the red carbon, which has a hydroxyl and a proton attached to it. So it's attached to 4 different groups. So those are 2 chiral centers. If we look at this one here, okay, I'll just help you out with this one. This is not a chiral center. Not a chiral center. Why? Because attached to 2 CH3 groups, right? This is a CH3 or a methyl. This is a CH3, and that carbon is attached to both of them. 2 groups are identical, so it's not 4 different groups. What about this carbon? If I highlight this carbon in red, would that be a chiral carbon? If it is a CH2, it's not chiral. A CH2 itself is not chiral. A CH2 can be used to distinguish between 2 chiral centers. Okay, a methylene itself is not chiral. So for example, this is not chiral, right? This is not chiral, all right? This is attached to this, which can be used to distinguish it. But in itself, it is not a chiral carbon. All right, hopefully that helps. Does that help a little bit? Okay. All right, cool. So with this carbon that I have in red, would that be a chiral carbon? Could anybody answer that? The carbon that I have in red, would that be chiral? Is it attached to 4 different groups? So remember, 4 different what? Groups. Is that carbon in red attached to 4 different groups? So let's see what it's attached to. It's attached to a hydrogen, which is on a wedge. Okay, that's not shown. A methyl. So let's write this down. So this carbon is attached to a hydrogen. It's attached to a methyl group. That's this one here. Okay. It's attached to an isopropyl group. So isopropyl. And then this group here, this would be a sec-butyl group. So it's also attached to a sec-butyl group. So that is definitely a chiral carbon. Okay, the one in red is definitely a chiral carbon, right? 4 different groups, right? If I draw in the hydrogen, okay, if I put this here, look, let's count. 1, that's a methyl. 2, that's a hydrogen. 3, that's an isopropyl. And 4, that's a sec-butyl. You look at the whole thing. Are those 4 different groups? Yes. So is that a chiral carbon? Yes, very much so. Okay, let's take a look at, if I highlight this carbon in blue, would that be a chiral center? Is that one attached to 4 different groups? The one in blue. I'll give you a second to look at it. Is that carbon in blue a chiral carbon? Yes or no? Is it attached to 4 different groups? Could anybody answer that? Is the carbon in blue attached to 4 different groups? Yes, it is. Okay, let's see what they are. We have the proton, that's in the back. So that's 1 group. We have a methyl group, that's 2 groups. We have an ethyl group here, and then we have all this spinach over here. So if you look at those 4 circles, you can see that those are 4 different groups. So yes, the carbon in blue is chiral. So the way that we tell that a carbon is chiral a lot of times is we put a little star by it. Okay, so this is chiral and this is chiral. All right, we got one more. Okay, if I highlight this carbon in green, let's say this one here, is that a chiral carbon? The answer is yes. Okay, why would this be a chiral carbon? It's attached to a hydrogen, which is in the back. So you get a hydrogen, you've got a methyl group, an ethyl group, and then all of this. So those are 4 different groups. So the carbon in green is definitely a chiral carbon. So we'll put a star by it. And if I highlight this carbon in blue, is that a chiral carbon? The answer is yes, right? It's got a hydrogen, which is not shown, but we'll draw it in here. So we have a methyl group, a hydrogen, we have all of this and all of this. So we have 4 different groups. 4 different groups attached to that carbon. So that is definitely a chiral carbon. So now we've identified chiral carbons and we're able to determine when a carbon is chiral and when it is not. So with that in mind, let's see if we can identify some chiral centers in vitamin D. Now this one might take you a little bit of practice to work through this one, but I'll highlight a carbon. So if I highlighted this carbon here, okay, this one in yellow, is that a chiral carbon? The one I have highlighted in yellow. Is that chiral? No, definitely not, right? Because it's a CH2 group, okay? If you don't remember, can't remember if we've gone over this or not. So a CH3, that's called a methyl. Methyl. A CH2, that's called a methylene. So it's not actually called a CH2 group, it's a methylene. And then if you have a CH attached to 3 bonds, that's called a methine, I-N-E, okay, not Y-N-E. So a methyl, methylene, and a methine. So right, Isaac, that's definitely not a chiral center because that's a methylene. Okay, Isaac, what if I did this one here, this one that I just highlighted in yellow? Would that be a chiral carbon? Exactly. It's not chiral, right? Because it's got two methyl groups attached to it. Isaac, what about this one? Or anybody? I'm just asking the same person. Anybody, but what about this one that I put on the far left? Would that be chiral carbon? The one on the far left, would that be chiral? So is it attached to 4 different groups? Yes, absolutely. This one is a chiral carbon. So we'll put a little star by it. Okay. It's attached to a hydrogen, which isn't shown, a hydroxyl. You have a CH2 here, CH2 here. You keep going for a point of difference. Here you have a CH2, and here you have a carbon that has 4 bonds. So this group and this group are different. So we have 4 different groups, and so that is a chiral carbon. Remember, you keep going until you find a point of difference. If there's no point of difference, then it's not chiral, it's achiral. But if you find a point of difference, it is chiral. So I'm just going to highlight the chiral carbons for you. There's a total of 5 of them in this compound. So there you go. So you can work on those in your own time and justify that those other carbons are chiral. So that brings us to the next topic, which is enantiomers. And enantiomers have a definition. Okay, so let's go over the definition. Some stereoisomers can be classified as enantiomers. Enantiomers are 2 molecules that are mirror images but are not superimposable and therefore not identical. So the 2 human hands, those would be considered enantiomers, right? Because they're mirror images, but they're not superimposable. Okay, so not superimposable and they are mirror images. So if I was to try to draw the mirror image of this chiral compound, right? This is a chiral carbon. Right here, how would I do that? Well, if I try to draw the reflection, it's going to look something like this. Okay, so this is the mirror image. So these 2 compounds are not identical, right? They're both chiral. They're non-superimposable mirror images, and so they are not the same. They are enantiomers. But if I wanted to draw the enantiomer, there's actually a much easier way to do it than the way I've drawn it here. The easier way is any wedge becomes a dash and any dash becomes a wedge. So if I redraw the compound like this, and I change this wedge here to a dash, okay, that would be the enantiomer. Okay, so these 2 compounds are identical, okay, and this compound and this compound, or this compound and this compound are enantiomers. All right, so to draw an enantiomer, you can try to draw the mirror image, but that's pretty annoying. It's a lot easier to just flip wedges and dashes. So it says here, often another easier way is just to flip the chirality center by flipping wedges and dashes. So here, you take this wedge, you turn it into a dash. Here you take this wedge, you turn it into a dash. By the way, if you took this compound and you replaced one of the hydrogens with a methyl group like this, that would be methamphetamine. Anyhow, crystal meth. Anyhow, that's neither here nor there. And these 2 compounds here, it doesn't matter if you flip the dash or the wedge because they're not chiral. Right? There's no chiral center in the compound. There's 2 methyl groups attached. So there you go. All right, so the next thing we're going to cover is designating a stereocenter as being R or S. So is a stereocenter an R stereocenter or an S stereocenter? And to do that, we use what's called the Kohn-Ingold prelog system. This is one of the most important things that you're going to learn in this chapter. So the way that we do it is like this. Okay, we look at our chiral center. Okay, so here's a chiral center right here. I'm going to draw the hydrogen in. Okay, and then what we do is we prioritize the groups based on atomic number. So remember, atomic number is the number of protons. Okay, so whichever element has the highest atomic number on the periodic table, that takes priority. So this carbon, which is our chiral center, is attached to a chlorine, it's attached to a hydrogen, it's attached to this carbon in red, and then it's attached to this carbon in blue. Could anybody tell me which one of these elements, is it carbon, hydrogen, or chlorine, which has the highest atomic number? It's not a trick question. It's going to be chlorine, right? So chlorine is going to be number 1, okay? Which one of these has the lowest atomic number? It's hydrogen, so that's going to be number 4. Now, if we look at the carbon in blue, what we do is we make a list of everything it's attached to going away from the chiral center. Remember, this is the chiral center, okay? So we don't consider the bond going back towards the chiral center. We only go away from the chiral center. So what do we have it attached to? Going away from the chiral center, it's attached to a carbon, and it's attached to this hydrogen and this hydrogen. So we make a little list, and we say carbon, hydrogen, hydrogen. We list them in order of atomic number. Now the red carbon is attached, we don't consider this bond because that's going back towards the chiral center. We go away, it's attached to 3 hydrogens. So we make a little list and we say 1 hydrogen, 2 hydrogens, 3 hydrogens. So if we look at the list, okay, here we have carbon, hydrogen, hydrogen. Here we have hydrogen, hydrogen, hydrogen. We just look for a break between the two, okay? And we see that the blue one has a carbon at the top, and carbon has a higher atomic number than hydrogen, and so that means the blue carbon takes a higher priority than the red carbon. So we go 1, 2, 3, 4. Remember, the hydrogen is always number 4 because hydrogen has the lowest atomic number on the entire periodic table. Now what we do is we go around the chiral center, okay? So the chiral center is here, okay? So we don't do things like this, okay? We go around the chiral center, either this way, okay, or this way. Okay, we go one way or the other. So here we're going to go from 1 to 2 to 3. So you see the direction that we're going is clockwise. So we're going in a clockwise direction from 1 to 2 to 3. And if it's going in a clockwise direction from 1 to 2 to 3, if it's going clockwise, we say it has an R, right? It's going to the right. So we say it has an R designation, okay? So that is in a nutshell how you do the Conn-Ingold pre-log rules. That's me teaching you my way, okay? Now, I'm going to show you with the other compound, which is it's an enantiomer, okay? We just flip this wedge to a dash. So this compound must be an S compound. So that means it's going to go counterclockwise. So here's what we do. Pay close attention. So what we're going to do is we're going to draw the hydrogen in here like this, okay? Remember, the chlorine is going to be number 1. The hydrogen is going to be number 4. We already decided that the ethyl group is 2 and that the methyl group is 3. So here's what we do. The way that I did it with this compound here, the lowest priority group, which was the hydrogen, was going in the back, okay? It's best to do it with the lowest priority group going in the back. If the lowest priority group is coming out towards you, like it is here, what you do is you read it, and this time it's going to give you R as well, but then if the lowest priority group is coming towards you, you reverse it. So we're going to go from 1 to 2 to 3, which is clockwise, which you think would give you R. But since the lowest priority group is coming towards us, right, it's on a wedge, it's not on a dash, we reverse it, and it becomes S. So this compound is an S compound. The one on the left is an R compound, and the one on the right is an S compound. So that is me teaching you how to do it. So here are the rules, okay? Number 1, you use atomic numbers prioritizing the 4 groups, 1, 2, 3, 4. It's best to place it in, or arrange the molecule in such a way that the lowest priority group is facing away from you. So oftentimes, not always, but a lot of times a hydrogen is the lowest priority group. So you'd want a hydrogen on a dash, not a wedge, because if it's on a dash, then it's going in the back. Okay, but it's not always. So remember, the lowest priority group, okay, not always, there's an ink you can see, it's not always hydrogen. It is a lot of times, but sometimes it's not. Then the next one is you count the groups going from 1 to 2 to 3 around the stereocenter. If it's going clockwise, it's R. If it's going counterclockwise, it's S. And of course, models can be really handy. So if you're wondering where the R and S come from, the R is for German for rectus, which is going to the right, and S is for sinister, which is left, okay? Anyhow, so with that in mind, this is kind of a crappy example for them to put in the textbook because they gave you one where the hydrogen is coming out in front, okay? But we'll use it anyway. We just remember that based off of this rule, if we have the lowest priority group coming towards us, so I'll write it down here. If it's towards you, or the viewer, you reverse R to S or S to R. And that's shown in the slides coming up. So here the lowest priority group, which is the hydrogen, is coming towards us, so we're going to reverse whatever the stereochemical configuration is. Okay, so if we look at the groups, chlorine has the highest atomic number. Oxygen has the second highest atomic number. Carbon has the third highest, and hydrogen has the lowest. So we go from, what were the rules? We go from 1 to 2 to 3. That's going in a clockwise direction, which would be R, but the lowest priority group is coming out towards us, and so we reverse R, and it becomes S. So this compound is an S compound. All right, and you see them walking you through it here. Now, these are David Klein's slides, okay? So this is from David Klein. He says what you should do is rotate the molecule so that the lowest priority group is going away from you. I'm going to put here, do not recommend. Okay, I do not recommend that you do that because it's usually where students are going to make a mistake. Okay, you can do it that way, but it says here, rotating the molecule leads to errors. I do not recommend it. Instead, what you do is read it the way that I told you, and then you switch it. So if it's R, it becomes S. If it's S, it becomes R. If the lowest priority group is coming towards you. If the lowest priority group is in the back, then you just read it the way that it is. Okay? So then when you have groups that are attached to a chirality center, you have to prioritize them. Okay? So if we look at the example that's shown here, we have this group versus this group. Which one takes a higher priority? Well, remember what I said is you make a list going away from the chiral center. So this carbon here is attached to 2 hydrogens, right, and a carbon, right? A carbon and 2 hydrogens, okay? So now, if we look at the carbon on the left, I'll do it in blue. It's attached to a carbon and 2 hydrogens. So 2 hydrogens. So there's no difference between the 2 carbons that are highlighted in green. So what we're going to do is we're going to go further. If I go to this carbon, it's attached to this carbon and 2 hydrogens. Okay, so this one is attached to carbon, hydrogen, hydrogen. Whereas if I go to this one over here, you can see it's attached to 2 carbons and 1 hydrogen. So it's got carbon, carbon, hydrogen. So where's the tiebreaker? It's right here. And so what does that mean? It means in the end that the group on the left, this group here, is priority number 2, and this group over here is priority number 3. So then we go from 1 to 2 to 3 like this, which is S, right? Because it's going counterclockwise, but the lowest priority group is coming out towards you. And so this would be an R compound, if that makes some sense. So this must be an R stereo center. Okay, you can see that they went through the list here. So again, you have to keep going until you find a point of difference, okay? And it's got nothing to do with the sum of the atomic numbers. You just go for the first point of difference. First point of difference. Do not try to tally up numbers or anything like that. That's not going to get you the answer whatsoever. Now, what if you have a double or a triple bond? In that case, if you were trying to prioritize this carbon here, remember, you go away from the chiral center, so it's attached to oxygen, oxygen, hydrogen. You count each double bond, or each bond of the double bond is a single bond. So you'd say it's attached to oxygen, oxygen, hydrogen, like that. Okay? So, again, I've gone over this rule with you. So with that in mind, let's see if we can assign R or S to this chiral center right here that I have highlighted in yellow. Okay? So I've got the hydrogen coming out towards us like this. I've got a nitrogen, so I'm going to use my green pen here. I've got a hydrogen, I've got a nitrogen, I've got a carbon here in green, and I've got a carbon here in blue. Okay, I'm going to give you like 15 seconds to see if you can come up with the stereochemical designation, and then we're going to work through it together. So give it a try yourself. All right, so let's walk through this one. Okay, we know the hydrogen has lowest priority, so it's number 4. Nitrogen has a higher atomic number than carbon, so it's number 1. And now what we're going to do is we're going to look at the 2 carbons. Okay, so if I look at the carbon in green, going away from the chiral center that I have highlighted in yellow, it's attached to oxygen, 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 right? 1, 2, 3 bonds to oxygen. Whereas if I look at the carbon in blue, going away from the chiral center, it's attached to this carbon, so carbon, and then 2 hydrogens. So carbon, hydrogen, and hydrogen. Well, obviously the oxygen is the tiebreaker. So that means the carboxyl group from the carboxylic acid, this is number 2, and this carbon is number 3. So now we I'll grab my green pen. We go from 1 to 2 to 3 around the chiral center. We're going clockwise. So clockwise would be R, but remember the highest priority group is not in the back, it's coming out towards us. And so the chiral center here is in fact an S chiral center. So there you go. So hopefully somebody got this, that this is an S compound. So usually I write an arrow to the chiral center, just write S. This is a compound you might recognize. This is called L-DOPA. Anyhow, all right. So if you're naming a compound and you want to put differentiate between 2 enantiomers, you have to put the stereochemical configuration at the beginning. So you see these 2 alcohols. One is R2-butanol. The other one is S2-butanol. This one down at the bottom, it's got 2 chiral centers. You've got a chiral center here, and you have a chiral center here as well. So 2 chiral centers. So in that case, you have to put a locant in front of the stereochemical configuration, R or S. But if there's only 1 chiral center, then you don't have to put a number in front of it because there's only 1 chiral center in the molecule anyway. All right. So let's try one more. Let's try this one here, the R2-butanol, and let's see if we can be sure that this is an R compound. Well, we've got a hydrogen going in the back. This is going to be the last priority. The oxygen is going to be number 1. Then we have an ethyl group over here, and we have a methyl group over here. Well, if I look at this carbon, it's attached to carbon, hydrogen, hydrogen. And if I look at this carbon, it's attached to 3 hydrogens. So this is the tiebreaker, which means that this carbon must be 2 and this carbon must be 3. So I go 1, 2, 3. You can see I'm going clockwise, and therefore this is an R compound. I can read it the way it's shown because the hydrogen is in the back. It's going away from me. So that is in a nutshell what the Kohn-Ingold pre-log rules are. And so now you have an idea of how to determine whether a stereocenter is R or S. And so before our next lecture on Thursday, what I'd like you to do is to get a little bit of practice on R and S. And then on Thursday, we're going to finish the rest of the chapter. We're going to talk about optical activity and what that means. Okay, so we'll go over optical activity. We'll talk about enantiomeric excess briefly, but I won't ask you to do any kind of calculations. Then we're going to cover the topic of diastereomers. Diastereomers are nothing more than stereoisomers that aren't enantiomers. That's all they are, really. And we've actually looked at examples of diastereomers already. I just didn't call them that. Then we're going to get into symmetry and chirality. We'll talk about what's called a meso compound. So we'll get into meso compounds. And then after that, we'll talk about Fisher projections briefly. And I'll show you how to do R&S on a Fisher projection. And then I think that's pretty much the end of it. Conformationally mobile compounds, we don't really cover this in detail, but I will go over it with you just so you have an idea of what it means. And then we skip the last few sections in the chapter. And so you can see we've covered the major part, the major concepts from the chapter already.